All right, chapter 7, the sections that we're going to be covering are all about probability. 7a in particular, called the fundamentals of probability, is basically an introduction to probability. Now, probability has a lot of different things that are involved in it. So when we go through these notes, you're going to start to realize that we're talking about a lot of different things. As you go from one problem to the next, it may just totally switch on what we're doing here, and I would encourage you when you're all done to go back through everything that you did in this section and try and mentally organize these individual ideas that we're seeing. All right, at the beginning of this, there's a little activity that you can try out. You don't really need to do the activity. It's a good activity, don't get me wrong. And doing this activity helps emphasize something that you'll see in another set of notes later on, because you'll do an activity in that one as well. But for the video that I'll do, I'm not going to mimic the activity. I'm just going to go ahead and get into the topics and go from there. The beginning of any introductory unit tends to begin with vocabulary. We have a few words here that we can talk about. Theoretical probability, we'll actually get to that one in just a little bit, so I'm going to hold off on that. What we're going to look at first is the outcomes and the events. Probability in general, I'm going to just kind of describe for you here though. Probability in general is looking at the likelihood of something occurring. Okay, something has taken place and we look at the likelihood that a certain aspect of it occurs. For example, like when you flip a coin, are you going to land on heads or are you going to land on tails? Type things. What's the likelihood that you get a heads or you get a tails? All right, now outcomes are described as the most basic possible results of an observation, like flipping a heads or a tails. Their example here goes a little bit further because it's going to say, imagine that you're flipping two coins. So instead of just flipping one, you're flipping two coins. There actually become four possible outcomes that are available. So these are all the things that can occur. When you flip the two coins, you could get heads, heads, both of the coins landing on heads. You can get tails, tails, both of them landing on tails, or you can get heads, tails, and tails, heads, which are actually different than each other. And we'll describe a little bit later why that is. I'll actually get out some coins and show you why heads, tails, and tails, heads are two different things there. But there's four different things that can happen when these coins are tossed, and those are all called the outcomes. An event is going to consist of one or more outcomes that share a certain property of interest. For the example that they're showing here, they're talking about, let me see if I pick out the number of heads that we can get. I think that's how they said it here. If we toss two coins and interested in the total number of heads. Can't remember if it's heads or tails. So the possible events that we can get here is when you toss the coins, you can get heads, heads. That would allow you to get two heads. If you toss either heads, tails, or tails, heads, you get one heads. Or if you toss tails, tails, you get zero heads. So the outcome can be what we actually see happen, but then the event can be this almost like analysis of, okay, well, how many times do we see heads as a possibility as well? All right, for our first practice problem, what we're going to do is look at an example that's going to help us distinguish the difference between outcomes and events. All right, it says, consider a family that has two children. Use capital B to represent a boy and capital G to represent a girl. Part A, let's list all the possible outcomes for the birth order, boys and girls, for a family with two children. Okay, so you want to put yourself in the place here and think you're having two children. One child is going to be older than the other, so there's a firstborn, there's a secondborn. Okay, what are all the different possibilities that we can have? We try to do these as systematic as we possibly can. First, maybe just go with, well, what if I have a boy and then another boy? So I get boy, boy. Okay. Next, what if I still have a boy first, but then my second child is a girl? So I have boy, girl. So I'm trying to be systematic and saying, well, let the first child be boy, and then the results, the second child after that can be a boy or a girl. So I get these two different outcomes, boy, 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 girl. Okay, so now I'm going to flip it around for the others. I'm going to say, well, what if I had a girl first? Okay. If I have a girl first, I could follow that up with a boy, or I could follow a girl up with another girl. So these end up being all four of the outcomes that we can get. Okay. Now, thinking of events, you try and pick out a characteristic related to the outcomes that we have. And here's a good example of it. If we're interested in the total number of girls, what are the possible events? Okay, we're interested in, well, how many girls could we end up with? How many weddings may we have to pay for, right? Something like that. All right, so from what we see here, the BB represents having no girls. That's a possibility. BG, GB are kind of the same here. They both represent having one girl. Okay, that's an event that we can have, which is having one girl. And GG would be the event of having two girls. So we have four outcomes, but if we're talking about the total number of girls, we actually have three different events that are possible. Where one of them, and we're going to talk about this stuff very soon here, one of them, the event of having one girl, is actually more likely than the event of the others, which you can see because there's two outcomes for having one girl where there's only one outcome for the others. Okay, now that we have a good idea of what outcomes and events are, we can start looking at probability in its numerical form. Remember that probability is the likelihood, so it's up here, is the likelihood of an outcome or an event. Okay, and we present this as a number. In this page, what we're going to be looking at is theoretical probability. So there's a few different types of probabilities that we're going to be talking about as we go through this packet. The big ones are theoretical and experimental probability. Okay, theoretical probability is probabilities it's not based on having done anything, but observing a situation and understanding all the different outcomes that are available with it. Okay, or all the different events that could be available with that one. Like generally flipping a coin, we always talk about that as like a 50-50 because you've got a heads and you've got a tails. Those are your only two outcomes. Okay, and you got a 1 out of 2 chance of getting heads, so we call like 50-50 or 50% probability. So some things that you've already heard, but it's based on what we know about the situation and not actually having done it. All right, this box that we have here is going to take you step by step on how you would calculate probability. I'm just going to go ahead and look at the very end here because this is visually what you want to see as your answer. When you calculate probability, its most basic form is going to be that of a fraction. The top of the fraction is going to represent the number of ways that an event can occur. So what we're interested in happening, okay, is going to go on top. And then on the bottom, you're going to see the total number of all possible outcomes that are there. Okay, that gives you a fraction. It's going to be part out of a whole. So how many times can the event that we want to see happen out of all possibles? That will become your probability. It can also be expressed as a decimal, and then later it can be expressed as a percentage, but in its most basic form, it's going to be a fraction. Example number 1 is going to take us back to the coin flipping situation. Okay, example 1 says, for example, the theoretical probability of flipping 2 coins and both coins landing on heads is 1 out of 4. Or you could read it as 1/4, but it might sound nice to call it 1 out of 4 here. Okay, and then these are all the possibilities, which briefly talked about before. We understand that when you flip 2 coins, they can both land on heads. Or if you flip a coin twice, it can land on heads and then heads again. Same thing with the tails. This part right here where one is heads and the other one is tails might be a little bit confusing on why that one counts twice. So for an example here, I have a couple of coins. I think what helps to understand the case is to realize that there's 2 ways to look at. One, if you're flipping the same coin twice, it's sort of like having children and you have an older child and then you have a younger one, so they're distinguished. You can also look at this as a case that you have 2 different coins that you're flipping. Okay, when I flip both of those coins, say I just flip them at the same time, they can both land on heads or they can both land on tails, what we had already understood. That one's got a bat on it. That's weird. All right, you can also get heads, tails, and tails, heads. So the quarter could be heads with a penny as tails, but there's this completely different outcome where the quarter is tails and the penny is heads. All right, so these two are actually different. Once we understand that the two coins are distinctively different for these, right? The first letter represents, in each of these, the first letter is the quarter and the second letter is going to be the pennies. You can also relate that to having children where maybe the quarter is the quarter is the first child and then the penny is the second child. Okay, so hopefully that made a little bit of sense there. Step 2, only one of the outcome results in both of the coins lands heads, heads. So I showed you the quarter and the penny both being heads. So now the main thing is if we understand that we do have 4 possibilities and we're interested on both coins landing on heads, that means heads, heads, that's what we want. We're going to ask ourselves, how many times does heads, heads show up in our list of possibilities? Well, it only shows up 1 time. How many possibilities do we have or outcomes do we have? We have 4 of them. So you set that up as a fraction and you get 1 out of 4. Okay, now 1 out of 4, 1/4 is a perfectly fine way to express your probability. If you divide 1 by 4, you're going to get 0.25. You can express your probability that way, or you can even move that decimal point 2 spots back and you can describe this as being 25%. And as we go through the activity, I think most of the time my answers are going to be in the form of a fraction, but occasionally I am going to be switching them into percentages. It's just, there isn't necessarily a right or wrong. Sometimes it just depends on what problem we're working on and what other things might, like maybe it's a multi-part problem and keeping them in fractions may be better, or I don't know, but you may see me just kind of change my answers as I go through them. Okay, so example 2 is, well, practice problem 2. And I got different names for all these things here. We're going to go back to the boys and the girls thing, which we can closely relate to the idea of flipping coins. Your firstborn child could be the quarter, and if it's heads, that means you have a boy. Your second child could be the penny, and if it's heads, then that means that you get a boy as well. Okay, but maybe you had a boy as your firstborn child, and then you had a girl. So you get boy, girl. Or maybe your firstborn child was a girl, and your secondborn was a boy, so you get girl, boy. Or maybe both of them were girls, girl, girl. Okay, so these are all your outcomes. It's pretty much the same thing that you're seeing with the heads and the tails, but sometimes with that question, it's a little bit easier to get right than the heads and tails because you understand there's a firstborn, a secondborn, and if you want to have a thirdborn and so on, you can do that as well. Let's see here. So they also brought in here at this beginning the events idea. So we're looking at the number of girls that you can have as our event. If you have boy, boy, then that's essentially 0 girls. If you had girl, boy, or boy, girl, then you actually got 1 girl. And if you have girl, girl, then that means you have 2 girls. So you can see that this event of 0 girls happens once, 1 girl happens twice, 2 girls happens once. All adds up to being the 4 events. That one counts twice. All right, what is our first question? Find the probability of a 2-family family having 2 girls. So this is as identical to heads, heads as you can get. We got Gigi 1 time out of 4 of them. So 1 out of 4 is going to give you that 1/4, which is the same thing as 0.25, which is the same thing as 25%. Again, I won't be doing that on every single problem, just kind of showing it here and there, because at some point I'll start throwing in some percentages and want you to know where it comes from. Question B, find the probability of a 2-child family having no girls. Right, no girls is only going to happen for the BB case. That would only be 1 out of a total of 4, so it's the exact same thing, just from and numerically it's the exact same thing, even though we're asking a different question. Okay, there's only no girls is the BB, and that only happens once. All right, so of course the next one would be, what is the probability of having exactly 1 girl? To have exactly one girl, it's either one of these two cases. So now we've got 2 outcomes out of a total of 4. So we're going to get 2 out of 4, which does reduce down to 1/2. Reducing, in most cases, yes is preferred. If you're doing a problem that has a lot of parts like A, B, C, D, like we're doing here, it might be in some questions better to leave these in like maybe a non-reduced form. But if you can, go ahead and reduce it anyway. It's a good habit. All right, so D, this is an interesting question because now we finally get something different than what we keep talking about from our little, I'll call them table that we have there. All right, find the probability of a two-child family having at least one girl. When it says at least, now that means that they can also have 2 girls. Okay, so that would be a family that's having 2 children. The mom just wants to have a daughter. Sorry for the boys, but she just really needs a daughter. So she doesn't mind if she's going to have 1 daughter or if she's going to have 2 daughters. So the probability of having at least 1 girl, go look up here. The only one that doesn't fit is boy, boy. These have 1 girl. This has 2 girls. So either those. So now that's going to give us a 3 out of 4 probability, which of course is the same as 0.75 and 75%, but I'll leave it like that for you. 3 out of 4. All right, for page 3, we're going to continue to hang out in the theoretical probability world. We're going to think about all the possible outcomes that we desire compared to all the possible outcomes available in just set of fractions. All right, we have a 6-sided die, and we roll it 1 time. What is the probability that the die lands on 3? Okay, so now I don't have a die in front of me, but you can imagine one. 3 is only listed 1 time on the die. It's got 6, right? 1 through 6, and the 3 is only listed 1 time. So your probability, theoretical probability of landing on a 3 is going to be that one event of a 3 out of all possible events, 6. There's your probability, 1 out of 6. Okay, now when that divides, I think you get 0.1 and then a bunch of repeating 6s. So this is a good one just to leave as a fraction. Yeah, so that way you don't need to get into the business of trying to round off decimals unless you really have to. So that's a great answer just there as a fraction. All right, B, what is the probability that the die lands on an even number? So now we got to think. We still got 6 possibilities, which is your denominator. But how many of the numbers on the die are even numbers? That would include 2, 4, and 6. You might obviously know from there that it's half of the numbers are even. But let's start with how many are there? There are 3 even numbers out of a total of 6 numbers. So your probability is 3 out of 6, which does reduce down to 1/2. All right, question 4. When I printed this out, I did print it out in black and white, but I'm pretty sure the original document's colored, if that's of any use to anybody here. What we are looking at is every single card in a standard deck of cards. There are 52 of them. Okay, you have, just for anybody who's not too familiar, I'll go over this a little bit. In a deck of cards, you have 4 suits. You've got the clubs, the spades, the hearts, and the diamonds. The clubs and the spades are going to be black colored cards. The hearts and the diamonds are red colored cards. So you can't see it in my picture here, but on the original handout, you should be able to see that everything in the bottom 2 rows is actually a red color. Okay, now within those suits, you have the same types of cards. You have ace, then you've got 2 all the way through 10. And after that, you have jack, queen, and king. So you have 1 of those cards per suit. You got 4 jacks, you got 4 10s, something like that. All right, I think we just go straight to the question now. What is the probability that a selected, the last part I was thinking is if you count these up, you're going to get 13. You can have 13 in every suit. That's a good one to know, and it'll save you some time as you're answering problems. 13 per suit, and you have a total of 4 suits, which is going to give you your 52 total cards. All right, A, what is the probability that a card selected at random is a jack of diamonds? Okay, so jack of diamonds is 1 particular card that's there. Within the diamonds row, there's a single card that would be a jack. So we're asking about drawing one particular card out of all of them that's here. That would give you a probability of 1 out of 52. Question B, what is the probability that a card selected at random is red? Okay, so now we know our denominator is still going to start at 52. How many cards are red? Well, the bottom 2 rows are the red cards. You got 13 and another 13, which is going to give you 26. So you have 26 out of 52, which is going to reduce down to 1/2. And I think, yeah, all I did is I wrote 1/2 on there, because you might realize that from the very beginning that the top half is black, the bottom half is red. The unreduced form, though, would be 26 out of 52, and just reduces down to 1/2. C, what is the probability that a card selected at random is an ace? Okay, so how many aces do we have in the deck? You've got 1 pursuit, so you've got a total of 4 of them. How many cards total do we have? We have 52, so we should begin with 4 out of 52. We have 4 aces out of 52 cards. That then reduces down to 1/13. As a little bit of a note, when you're working with the cards and being asked questions, the 4s and the 13s are going to show up quite a bit as we're going through these things. And you might start to memorize that 4/52 is going to reduce down to 1/13. It just happens often enough. I might as well point it out to you. All right, switching out of cards for just a moment here. What is the probability? So we're still doing theoretical probability. What is the probability that a randomly selected person has a birthday in December? Okay, note that the month of December has 31 days, and let's assume that a year is worth 365 days. Okay, so we don't have a leap year here. All right, all possible days in which you could have a birthday in December is 31 days. All possible days that you can have a birthday throughout the year is going to be 365, so we're just going to use those numbers, and that's pretty much the end of it. I don't think that that reduces down to anything. 31 is it's a prime number, and we don't use it too much. Yeah, if I divide those, I'm going to get this goofy looking decimal that goes there, so not really gonna, it shouldn't reduce into anything special. Yeah, it does not. All right, so that would be the answer. The only thing about this question is don't try and get to go off script on it and do something like 1 out of 12, because the months do have a different number of days in them. So we need to think particularly about the number of days that are in December compared to the 365. Don't do 1 out of 12 for that problem. All right, usually when I teach probability, I start with the graphic that we see at the top of the page. It's not a big deal that we didn't, but sometimes I like to start with that because what it does is it gives you a range of values that are allowable for probability. Okay, so the values for probability are actually very restrictive. The lowest that you can have for a probability is 0, where the highest is going to be a 1. This, of course, would be in the decimal form of numbers. The percentage forms of these would be 0% to 100%. Okay, we've done other things in the past where percentages can go over 100%. That is not the case in probability. To have 100% probability, or a probability of 1, means something is absolutely going to happen. There's no beyond that. It either happens or there's a lesser likelihood that it will. But once it happens, the end. Okay, so that's the top end of it. You can also relate this to the fractions that we've been setting up. If we ever came across like a fraction that was a 4 out of 4, that would be 1 whole, which puts you at the top end here. Okay, and then you could have a fraction that's all the way to like 0 out of 4, which would mean that you have a 0 probability. Then everything in between is sort of a scale of its likeliness. The middle, we call it 50-50 sometimes, 50% probability. It is just as likely to happen or not happen. The closer that you move to the 1 becomes more likely, and the closer it moves to the 0 is the less likely that you could get. Okay, so number 6. What we're going to do in number 6 is we're going to see a sample of getting the answers on the extreme cases. You're also going to look at a couple of answers that are in the in-between area. Okay, a fair die is rolled. A die has the sides 1, 2, 3, 4, 5, 6, so a basic die that you know. What is the probability that the die lands on a number less than 7? Well, if you look at all the different sides that we have there, all of these numbers are actually less than 7. We don't have a 7 there. We don't have anything bigger than 7. So they're all going to be less than 7, which means we have 1, 2, 3, 4, 5, 6 outcomes that are allowable for this to be successful. That's your numerator 6. And you also only had 6 outcomes to begin with. So you're going to end up with 6 out of 6, which evaluates as a 1, or you can call it 100%. So this is absolutely certain to occur that you'll get a number less than 7. Okay, what's the probability that the die lands on a number greater than 7? Now, there's no numbers on the die that are greater than 7, right? So it's 0 possibilities out of the 6 that are available, which means that you get 0 or 0%. Okay, so those are the extreme cases. C, what is more likely, which is more likely, that a die lands on a number less than 3 or greater than 3? So now this is a little bit better of a general question because, you know, it's not the extreme cases here. 3 is actually a number that is in the list that we have here. Okay, so the first one, number less than 3, okay, there's only, I want to make sure it doesn't say less than or equal to, it just says less than 3. That's going to be the 1 and the 2. So less than 3 is 2 possibilities out of the 6. Less than 3 or greater than 3. So greater than 3 is going to be 4, 5, and 6, which is 3 out of 6. Okay, so this one is going to be the more likely one. It does simplify to 1/2. There's a 50% chance that you'll get a number greater than 3. This would simplify down to 1/3, so there's like a 33% chance that you'd get one of those numbers. All right, the next part that we're going to look at, kind of just squeezed here in the middle. I'm actually not going to look at the video, I'll just let you read it. It just talks about rounding with probabilities and take what you can from it, okay? But I'm not going to spend any of the video time going over that. All right, now what we're going to do is leave theoretical probability behind for just a little bit. We're going to talk about another thing which is called relative frequency probability. I also refer to this as experimental probability, so if I happen to mix up the words as I'm going through it, it's just, in some topics there's different vocabulary for things. So if I say experimental probability, it's the same thing as relative frequency probability. So a term I'm not as used to using when I talk about probability. Okay, so how does it differ from theoretical? Theoretical is you thinking about all the outcomes that are available and then setting up these fractions. Relative frequency probability is taking data that was collected, using that data to decide what probabilities would be there. So something has actually happened, some data has been collected. I'll try not just to make up a whole bunch of stuff and keep to what they say here. Example 2, if we observe, that's one of the key things, you're just watching stuff, you're getting data. If we observe that it rains in a certain city an average of 124 days per year, we might say that the probability of rain in that city on a randomly selected day is 124 out of 365. Right, there's no reason for us to theoretically come to that conclusion, that that would be the probability. But over the course of a year, we saw that it rained 124 times. And then there's whatever number, if you want to subtract it, whatever number of days where it didn't rain, but it was 124 out of 365 days. So we could use that as our probability to evaluate any future days as we go through the year. Okay, number 7. You may have heard of the term 100-year flood. This means that a flood of that magnitude has a 1 out of 100 chance of occurring in a given year. Right? A 100-year flood happens every 100 years, so once out of 100 years. Suppose that geological records indicates a certain river has crested above a particular level 4 times in the past 2,000 years. Based on the relative frequency method, what is the probability that the river will crest above this flood level in any given year? Okay, so now we're not talking about the 100-year flood. We're looking at some new data. 4 times in the past 2,000 years, it's exceeded a level. So we literally just take those numbers, say 4 out of 2,000, and then we evaluate and we convert as we might need, or you can reduce if you want. The way that I went with the answer was not just reducing it down. I think reducing it's going to be 1 out of 500. See if my mental math is on point today. 4 divided by 2,000. Yeah, got it right. All right, would be 1 out of 500 chance. So you could do that as an answer if you want. My preference, I guess, is to divide that one, and when you divide it, I know I have it on my paper, but I'll just type it in again. When you divide it, you get that, so that'd be a decimal form of the answer. And then you can convert that decimal into a percentage by moving the point 2 spots over. Just please be careful about, if you are going to do percentages or decimals, that you understand when the percent symbol goes on there. The decimal form is what you get directly from the division. That will be a number between 0 and 1. Okay. If you want to change it into a percentage, you're going to need to move the decimal over and add that symbol on there. Do not forget to add that symbol on there. All right. Should we expect the relative frequency probabilities to be the same thing as the theoretical probabilities? No. Relative frequency probabilities are based off of experiences and something that's happened, where theoretical is based off of our ideas. Okay, as an example, if you have a coin that you're flipping, I know the example is going to bring up using 2 coins here in a minute, but if you just have a single coin that you're flipping, just because it lands on heads right now doesn't mean my next flip is going to be on tails, and then heads, and then tails, and then heads. There's not going to be a perfect balance. It is possible, if I'm going to look at flipping the coin 10 times, it is possible that it's not going to land on heads 5 times and tails 5 times. It could land on heads 9 times and only land on tails once. It's a reasonable thing that can happen. Okay, they do not need to be the same thing. Which one is better, theoretical or experimental? I suppose it really depends on what we're talking about. I mean, if there's a good theoretical probability, like rolling a die, flipping coins, you try and stick to those as your probabilities. But experimental, you could run an experiment and find out it's not the same. However, we're not talking about in this set of notes, but we can get to it a little bit later. There's something called the law of large numbers. That when I do flip the coin 10 times, you might get something like 9 heads to 1 tails. But if I were to flip it 100 times, it's going to start to stray away from that direction. You're not going to get 90 heads and then 10 tails. It could, don't get me wrong, you can. But as you continue to flip the coin more and more times, it is going to start to balance the number of heads and tails. We're talking about maybe flipping it like 1,000 times though. Okay, so it's called the law of large numbers, if I can say that right, the law of large numbers, and we'll dig into that a little bit more later. Okay, for question 8, we're going to be flipping 2 coins. This activity really seems like 2 coins at a time, and they're going to do it 100 times. That's a total of 200 flips. Not that that's too important, but they do flip the 2 coins, so it's like my quarter and my penny. Here I color coded them, but you can think of them as the purple one is my quarter, and then the red is my penny there. All right, and we flip them 100 times. We keep flipping them, and 49 of the times, which is basically half of that number, half of the time it landed on heads. Should we have any reason to suspect that the coins are unfair? Now that seems to be somewhat of a dramatic choice of words, so that they're unfair, like you're being cheated, but just kind of roll with it. Thing is yeah, we should expect that there's something off in this situation, because when we look at all the different outcomes that were available for flipping the coins, with the quarter being the purple one, it could be heads or tails, and then the penny being heads or tails. We actually have 4 combinations. Remember, heads, tails, tails, heads, tails, tails. And heads is only 1 out of all 4 of those. So we should have expected, if we flipped the coins and did this whole thing, that the number of heads should have been around 25. 24, 23, 20 would be all right, 30 would be all right. 49 has started pushing it into a weird direction. Now, why would the coin be unfair? I don't know. What we're trying to get you to understand is that we should trust the theoretical probability. So even though the experimental is not always going to give you the exact same thing as the theoretical, it should tend towards that theoretical that we know. Okay, subjective probability. I'm not going to talk about it. You can read over it and see what it is, but for the most part, it doesn't really lend to any calculations that we'll be doing, so I'm not going to spend any additional time talking about that one. The next part that we have is the probability of an event not occurring. Okay, heads up, this is going to be helpful when we get to talking about odds. Okay, but look, the probability of an event not occurring is the opposite probability of it actually happening. So we've talked about what's the probability that you roll a 3, what's the probability that you flip heads. When we say what's the probability of you not flipping heads, we mean what's the probability of every other thing happening that'd be there. What we should see, and I think I'm just going to jump around through the answers here. What we should see is that the two answers that we get complete each other to make one whole. Because something is either going to happen or it's not going to happen. There's no other thing. It can happen or it cannot happen, I should say it that way. Okay, so these are going to add up to 100%. What's the probability that you're going to draw an ace out of a card of decks? It's 1 out of 13. That actually comes from the 4 out of 52 that we did earlier, but reduces down to 1 out of 13. Okay, so what's the probability that you're not going to get an ace? Well, if you get a 1 out of 13 chance of getting an ace, and you subtract 1 from 13, you get 12. That means that there's 12 out of 13 possibilities of not getting an ace. Underneath that, we just see the addition that these two things, the probability of an event and the probability of not an event, should add up to being one whole. Mostly that should be an intuitive idea, but we want to make sure that we outline it. This is a little bit of a neat equation, I guess, at the bottom here, though. Probability of something not occurring. You can take 1, which means absolutely happening, and if you subtract the probability of it occurring, that leaves you with the probability of it not happening. Right, so that's us taking like 13 out of 13, one whole, subtracting 1 out of 13, and you get 12 out of 13. Okay. Now, we're not seeing this in application yet, but I know that there's another time where this is going to come up, and using that as an outline to answer the problem is surprisingly helpful. All right, question 10, following up on the probability of not having an event. There's your little equation at the top. It's just going to be 1 or 1 whole minus what the probability of an event happening would be. Okay, so when drawing a single card at random from a deck of 52 cards, what is the probability that we do not draw a heart? We do not draw a heart. Okay, well, hearts make up 1/4 of the deck. So if we take our 1 whole and we subtract 1/4 of the deck from there, we end up with 3/4. And that's all there is to it. B, if today's forecast predicts a 0.37 chance of rain, that means 37% chance of rain, what is the probability that it will not rain today? Well, if there's a 37% chance that it's going to rain, take that away from 100% and you get 63%. A 63% chance that it will not rain. We'll box that one. All right, next we're going to talk about probability distribution. In this case, we're looking at 2 dice now being rolled. Okay, and there's a lot of things that you can do under a circumstance of this, but think about it like a board game. And if you're rolling dice, you're rolling 2 dice. What you tend to do is you add them together, and it tells you how far you can move on the board. Okay, so here's a table that, when set up, shows you all the different sums that you can get from rolling the dice. If you roll a 1 and a 1, you're going to get a 2. If you roll a 2 and a 1, you're going to get a 3, right? 2 plus 1 is 3. But check this out. If you roll a 1 and a 2, you also get a 3. So again, it's important to understand that these are 2 different dice. that you have here. It's like my quarter and my penny. Okay, so rolling a 2 and a 1 is actually different than rolling a 1 and a 2. You can pretend that they're colored dies where all the first numbers represent a green die and all the second numbers represent a blue one. So you got to understand that some cases are fairly unique, like let's go way over here, like 3 and a 3. That only happens once. But you can get a 2 and a 3 two different ways, depending on which of the dice rolls the 3 and which one rolls the 2, and then you have the flip-flop of it. So that can happen twice on there. Okay, but anyway, here's a whole table of all of our sums. You just match everything up, like I match up the 4 and the 5. So 5 and a 4 is a 9, so I got that. And then your largest number that you get is the 12 from the 6 and the 6. When I filled this in to complete the table, I tried to make them color-coded between red and purple because there is this diagonal striping, I guess, of how the answers are. You've got the 2, then there's 3s, there's 4s, then the 5s are all going to go that direction. There's the 6s. 7 is going to be the most common one that you get by 1. That actually happens 6 times. 7s. Then it continues to count up. You get 8s, you get 9s, you get 10s, you get 11s, and then you get less from there. So the number of sums that you get, like 2 to 3, it's increasing up until you get to 7, and then the quantity of those starts to decrease in there. Okay, and now what you can do is you can take that data and you can put it into a table that looks like this. We'd seen this kind of with histograms because we did see frequency in there, but you list all the events that we get, like the sums of 2s, all the way a sum of 12, the number of times that that has occurred, and then you can change that into a probability by simply taking the frequency and dividing it by the total number of outcomes. Here's where you gotta be a little careful. You're not dividing this number by the number of rows that we've got here, but you're dividing it by the number of little squares that we see, because all of these are different possible outcomes that can occur. Okay, so you would divide 1 by 36, you divide 2 by 36, 3 by 36, and so on, and get all that filled in. The only reason I did some of these in red was just to match the, and I may have mixed them up there. I was trying to match them up to the table that I had. Oh, I did. All right, sums of 7s, I did purple. Sums of 6s, I did red. But it might get confusing looking at some of the numbers in there, but I was trying to match them up to the table. That's all that is. All right, at the bottom it says, notice that the sum of probabilities listed is always going to add up to 1. And that's just right over here. Sort of like your cumulative frequency. So if we want to make some connections to histograms, your frequency should add up to all of the outcomes that you get, and your probabilities, if you add those all up together, should add up to a total of 1, which is the same thing as 100%. So sometimes these will be written as percents, sometimes they'll be decimals. Remember, you can express things however we really want. You can even express them as fractions if you want. Okay, question number 13. This one is a bit of a jewel that's kind of just dropped in here in the activity, and a very, very useful thing, and I don't want it to get overshadowed by all the other stuff that we've needed to talk about. When we do probability, sometimes we're just interested in a real quick thing. We're gonna reach into a bag and we're gonna draw out a name. Maybe we're doing door prize and draw a name. What's the probability somebody's name is gonna get drawn? Sort of thing. But there's a lot of other cases where we're interested in a combination of probabilities back to back. What if we reach into that bag and we draw out 5 names? Okay, what's the probability that the first name is going to be Bob, and the second name is going to be John, and the third name is going to be Sophie, and so on? When we start looking at like a continuation stuff. Okay, so let's kind of go back to the beginning when we were looking at a family with 2 children having boys and girls. What's the probability that you're going to get a boy then a girl? What's the probability you're going to get a boy and then another boy sort of situation? Okay, here's the hardest part about that is trying to figure out what your denominator is. We can almost like count the different things that we that we need in our numerator, but the denominator, trying to figure out how many total possibilities there are, especially when we have light. I mean, what if you're going to have 5 children? Well, how many different combinations can you create with 5 children? Well, here it is. What you do is you think of every moment independently here, right? So we're getting back to having children. The first child you have is it's the first occurrence. Then you're going to have another child and then another child. So we're doing 3 children here. When you're having that first child, there's only 2 outcomes that are available at that time. You can have a boy or a girl, the end. Okay, now you want to look at the second child independently of the first one. How many different genders can you get second time? You can still get a boy and a girl, so it's still 2. The third time, same thing. It's like every time you have a child, you're flipping a coin, either heads or tails, sort of thing. And they don't depend on what happened before. Just because you had a boy the first time doesn't mean you're more likely to have a girl the second time or anything like that. You need to look at them as individual events. Sorry, I just caught myself using the word events as the way that I normally do it, where an event is an action that's taking place. Okay, a different use of the word event in this activity here. Okay, but anyway, you look at each of these times as their own, and you ask, well, how many outcomes are available? And then what you do is you just multiply them all, and it tells you the overall number of outcomes that would be available. So for having 3 children and thinking about all the different combinations of boy, girl, etc. From there, there's actually 8 different combinations, because there's 2 in the first, times 2, and there you go. Now, here's a graphic that will go along with it. And see, the thing is, you really don't want to have to draw a graphic if you're getting into having 4 or 5 children, because these things get big fast. Let's take a look just at the beginning part here. First, you can either have a boy or a girl. If you do have a boy, then following having a boy, you could have a boy or a girl after that. Or maybe you started with a girl and then your second child's a boy or a girl. So this actually gives you 4 different possibilities: boy, 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 girl, boy, girl. They create these little paths that give you sequences. Now, that's for having 2 children, so you can see there's a total of 4 paths that we'd already mentioned before. Okay, as soon as you have a third child, you want to go to the end of one of these. So boy, boy, at the end of that one, you can either get a boy or a girl. If you had a boy, then a girl, you can still get a boy or a girl after that. So each of these is going to branch off 2 more times, which is going to give you a total of 8 different paths. All right, so there are 8 different sequences shown. For example, we could look at the one that's girl, boy, girl. That one would be having a girl first, then a boy, then a girl. It's this path here. But you know, there's these other ones, right? There's girl, boy, boy, girl, boy, girl. There's a total of 8 different paths, and maybe you can see in the numbers why we do the times 2. We start with 2, then those each double their paths to 4, then those all double their paths, which get us to 8. So if you're going to have 4 children, you'd have a total of 16 possibilities, and you just keep multiplying by 2 from there. All right, now let's take this data, put it into one of these charts. Let's suppose we're interested in the number of girls that we have. Okay, so what is possible? So nothing really goes in this blank. I just put the letter N. It's more or less just a title, but I put the letter N in there. These are the values that we really want. Okay, so if you are having 3 children, at most you can have 3 girls. It's possible, but there's only one way that can happen, which is girl, girl, girl. Okay, only one way that can happen. On the other extreme, way over here, having no girls happens when it's boy, 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 and that can only occur once from all of our little paths. Okay, and then these are more interesting ones. Try and find them in there. Having 2 girls, going back up to the chart, if I started up here in the top, having 2 girls would only be GG right here, boy, girl, girl. So I got one of those. 2 girls from the bottom, you can have girl, boy, girl. You have girl, girl, boy. So then there's 3. Then you can do the same thing for 1 girl. Find all the paths that only have 1 girl in there, and there'll be 3 of those. Of course, these should add up to 8 because there's a total of 8 different paths that were available. So if you're missing one or you got more than 8, then something would be incorrect about your table there. What I noticed here was when I filled in the table, I actually just put the values of the frequency for each of those and not the probabilities. So technically, they should be divided by 8 each. All right, question 14 is sort of like us going back to our two-way table and then looking at data expressed that way to calculate probabilities. Let's see, this table shows the gender and the political parties of 100 delegates at a convention. So there should be a grand total of 100 that we see here. One thing that I did at the beginning is I went ahead and started making totals for things like if I had the 21 and the 28, I'm going to get 49. So there's a total of 49 Republicans. And if I add these numbers, I get 41. So total number of Democrats, independents 10. And then I checked that that when I added these together, that I did end up with 100. So 49 plus, let's see, together that's 51. So 51 and 49 is 100. So it does add up correctly. And then also added vertically for the women and the men, just in case I need those numbers, which you do. All right, what is the probability that you will meet a man? All right, so out of everybody that's there were 48 men, right? And there was 100 people there, so 48 out of 100 will be 48%. Question B, what is the probability that you'll meet a Republican? There were 49 Republicans out of 100, so 49. So if it wasn't out of 100, then you could just set it up as a fraction or you could do some division. But being that it is based on 100, those numbers are really easy just to change into the percentages. What is the probability that you meet a male Republican? Okay, so that one doesn't require any adding here. Male Republicans are 28, so 28%. What is the probability that you meet someone who is not a Republican? All right, so Republicans were 49. Not Republicans will be Democrats and independents, which will be these numbers added together, so 51%. Again, that question's a little bit easier because you do have a total of 100. Any other number, you might need to do some math. If it was like 200, then you would just cut all your numbers in half and you get your percentages. But I want to make sure that everybody sees that this was a little bit easier to do because the total was a 100. All right, we are in our final stretch here. We're going to talk about odds versus probability. I guess we'll give you a little bit of information in case you want to go do a little bit of gambling sometime soon. All right, odds. There's two different ways you can say odds. Well, to start with, and then we're going to throw one more at you. Two different ways you can say odds. The odds for an event or the odds against an event. Now, for the most part, they're the same thing. And if you look at the two fractions that we get, they're just reciprocals of each other. The odds for an event is going to be the probability of the event divided by the probability of not the event. Okay? The odds against are going to be the reciprocal probabilities of not the event over the probabilities of the event. Okay, so pay close attention to that. Most often we're going to be going in this direction, just as a heads up, but these are reciprocals of each other. All right, suppose at a legal gambling house, a player wins a game if 2 dice are rolled and the sum of the dice is 7. We did talk about how 7 was the more common sum that you could get by just a little bit. What do we want here? Assume that fair gaming is practiced at this legal gambling house. For the problem, you may wish to refer to the probability distribution. That's what I just referred to there. Okay, so A, when rolling 2 fair dice, what is the probability that you roll a sum of 7? That was 6 out of 36. Let me see if I can find it. To get a 7 was anything along that diagonal, which was 6 outcomes out of a total of 36. Okay, when rolling 2 fair dice, what's the probability that you will not roll a sum of a 7? Well, if it's a 6 out of 36 chance of getting 7, then it's a 30 out of 36 chance of not getting a 7, because those two numbers have to add up to that denominator of 36. Okay, so now we've got the probability of and the probability of not. So if you were asked to figure out the odds for rolling the sum of 7, going back up here, if If you're asked the odds for, that's going to be the probability for over the probability of not. Probability of over the probability of not. That's probably a better way to say it. So we're going to take probability of it happening, 6 out of 36, dividing by the probability of it not happening, 30 over 36. Basic mathematics. These have the same denominators, they just cancel out. There's a method called keep, change, flip. There's a lot of things you can look at, but I can go ahead and tell you that in every problem we're looking at, because of what we're doing, the denominators are going to be the same, they are just going to cancel out. So it'll immediately simplify down to 6 over 30. That then reduces to 1 over 5, which in this problem you would read as 1 to 5. Because we're talking about odds here. We're going to read this as a 1 to 5 odds. So the odds against. The odds against are just going to be the reciprocal of that. We would have started with a 30 on top of the 6, which reduces down to 5 over 1, that we read as 5 to 1. Okay, note at the bottom here. The house must pay winnings to players if the sum of 7 is rolled. So the house is interested in the odds against this happening. They are going to be interested in this setup here. So sometimes they're going to use the phrasing, the odds on, but when they say that, they are meaning the odds against. So in a lot of the problems, you're going to read them, they're going to say the odds on such and such. You want to think of that as the odds against. Make sure you have the not probability on the top, then you have the probability of on the bottom for it. And if you do that, it'll make it a little bit more consistent for when we do the calculations on your winnings. All right, now we're going to take a look at how to figure out how much money they owe you if you win. All right, we are doing the same game. The odds against rolling a sum of 7 will be a 5 to 1. Okay, all that's from what we just did. All right, now what that means, what that means is that if a 7 is rolled, the player will win $5 for every $1 they bet. That's how we interpret the 5 to 1. A player will win $5 for every $1 they bet. So you want to win more, bet more, you can do that. All right, so what we're going to look at is a breakdown of just doing calculations. What if you don't bet $1, right? What if you bet $3? Okay, so let's say we bet $3 on this thing and we actually win. All right, A, since the odds against rolling a 7 are 5 to 1, if the sum of 7 is rolled, the player will win $5 for every $1 they bet. That's coming up from the description at the top. Okay, if you place a bet, a $3 bet is the same thing as placing a $1 bet 3 times. I think that makes sense. So if a 7 is rolled, the player will win $5 3 times, which means they win $15 from there. All right, now we'll come to this one in a moment. For the most part, you can do all that calculation as what's called a proportion. Once you've got your fraction, that would be your odds against or your odds on, so 5 to 1, and you have it right side up. This is helpful here. If you have it right side up, you've done it the correct way. It was the probability of not versus probability of. Then what you can do is just place your bet in the denominator of this other fraction. That's where your bet goes. Your bet goes there, and then you can call this x, and you can use cross products to solve for x. Cross products would be multiplying the 5 by 3, which would give you 15. Then 15 divided by 1, you always divide by the other number. 15 divided by 1 is going to come back as 15, so same answer. That might not look like much here because you have a 1 on the bottom, but if you had like 5 to 2 odds, you'd have to multiply and then divide by 2. Okay, so how much are you going to get paid? How much are you going to get paid? I kind of hate that we throw this question at you because it's just a little sneaky thing there, but there's a bet that's made so that if you lose, they keep your money, right? It's not a verbal contract that you've made. You've handed them some money. So when you do win, they're not just going to give you back your $15. they got to give you back your $3 original bet. It's like your deposit that was in there. Okay, so when you do win, you don't walk away with, like, they don't pay you back $15, they pay you back $18. Give you back your bet plus what your earnings were on there. Personally, I kind of hate that we do that because your winnings are $15. I mean, that's really what you're going to remember from all of that is you won $15. But technically, they are going to hand you $18. All right, so for our very last question here, at a horse race, the odds on, see those words there? The odds on a horse named Blue Moon are given as 7-2. So we didn't even need to calculate it. They just told us that the odds on are 7-2. Make sure that the 7 goes on top, the 2 goes on the bottom, so that way we can put our bet down here and just do some cross products. If you bet $10 on Blue Moon and Blue Moon wins, all right, he's gonna win. So we bet $10 and he wins. We can put the 10 there, call this X. We can do some cross products. 7 times 10 is 70. Divided by 2 is 35. $35 are your winnings. How much money will be paid out to you? See how we throw that out? How much will be paid out to you? Well, you can get your $35 winnings plus, what did you bet? $10. So the final answer is $45. You won 35. Let's be clear. You won $35, but you're going to get paid back 45 because they got to give you back your $10. All right, that is your introduction to probability.